Hello friends, welcome back to another episode of the Raytracer challenge by James Buck, where I implement a ray tracer following along this book here, which you can't see due to my virtual green screen there, this one, in Rust, a language which I am currently learning while actually implementing this thing. And for me, it's been 2 weeks now. I've been on a short vacation since I did the last session. I prepared one in advance so that you could see it while I was on vacation. So please bear with me if I'm not 100% up to speed to the topic at the current moment, because it's just some time gone by. Today is, by the way, another bonus session where I'm doing something or trying something which is not part of the book, because I want to play around with WebAssembly. I want to actually compile the current ray tracer we have, which is by far not finished. We will go on later on and implement other chapters of the book and make it even fancier and better and nicer and allow better rendering and other techniques and stuff. But I want to try something which I have read about a lot, that it might be quite easy to compile Rust code to WebAssembly. And I want to do this. For those of you who do not know what WebAssembly is essentially a standard binary language, some sort of assembly language, which is especially made as an interchange format for different systems, so that it can easily be executed in all different kinds of virtual machines, which are then able to execute this code. And especially browsers are, of course, part of this, which is why web is in the name. But in the long run, it might even be possible for completely other and different systems to execute WebAssembly, because it's more or less just an interchange binary format, which should be, in theory, easily executable and even translatable to native code for different system architectures and so on, to be optimized and run there. So we don't want to take a real close look at what WebAssembly is. We want to simply use it, because there should be the possibility in Rust to compile our code, which we've written so far, our ray tracer in Rust, to a WebAssembly package, which then should be loadable in the browser. Then we will need to write a certain kind of a little bit of JavaScript glue code and bridge to put it all together, to render our ray tracing data live while it is being rendered into a canvas. At least that is my goal for today. Let's see how long or how good we will be able to get along there. I've actually researched this topic a little bit before, which is, by the way, has happened before my vacation as well. So I'm not 100% sure what I did and what I didn't get to work until now. But we will actually see that in a second. So I have played around a little bit with WebAssembly. You can see this. I've this package here called WASM bindgen, but I thought, as I'm not even 100% sure in which state this experiment of mine is, and it definitely didn't work when I left it there to be worked on. I thought we might simply start fresh and take a look at this, how this works and how we are going to get this to work, while having this as a reference, as a starting point, more or less. So I'm simply copying now my let's get to the other directory here, and then let's copy the Raytracer challenge folder to something which we might call WASM experiment, for example, just to have it as a reference there. We are missing a -r here, so let's copy this over there. And then let's go back into our main folder and let's simply check out our master branch here, main branch here, sorry. Yeah, and there is a change, I guess, I made to the WASM README. Let's just stash this one and check out the main branch again. There we are. And now let's clear this. And do we have something? Only a subset of git fixture. Okay, I see. Yeah, there's now this folder which we will remove for now. I guess we will create it later on. And now we should have a clean state, which is exactly the state of the latest of our latest video. So let's take a look. Okay, let me quickly open up the experiment here in a separate window. I have now here off screen. I can actually move it on if we need it, which I will do. And then let's take a look there and try and get this to work. So what I've done so far is I have found out that we need something called WASM bindgen, or that we want something called WASM bindgen, which is essentially a high level. Wasn't there a website? Yeah, which is essentially a high-level set of libraries as well as macros to easily interact with JavaScript on the one hand and have Rust on the other hand, and that is something we definitely want to have. So let me get this here, which is now we simply can add all this stuff to our cargo toml file, which I have more or less, if I remember correctly, copied from the page and put all together. We will take a look at this in a second. Let me simply copy this one here. Okay, let me move this out of the way again. And then let's take a look. We need this stuff now here. I've actually put all of that there. Rust analyzer failed, cargo metadata. Okay, there may be some problem here. We will see. So let's move this console out of the way. And maybe let me rearrange my windows here a little so that I can see something else here. Okay. So yes. So what have we done here? First of all, I guess this was a change. I'm not 100% sure why we did this. I'm not even sure that this is a change. Maybe I should have taken a look at what we had here before. Okay, we didn't have this there before. I guess I copied that out from some documentation. Furthermore, I defined that we want a console error panic hook. I guess this was one which allows us to print errors or panics of the Rust code directly into the JavaScript console later on. Then we have this bindgen test stuff here. We are telling the compiler here just for the release to optimize our code a little. Essentially, I've changed this. It's not optimized for small code now. It's optimized actually for speed because I'm not very concerned that our ray tracer will, if it will be, I don't know, 100, 200 or 300 kilobytes. I don't care about that. I want it to be fast because it is a very, as you know, CPU and calculation intensive task to be used. So that is that there. These are our dependencies from before, all the ones we used, simply available there. And now our WASM configuration stuff begins. Here's our WASM bindgen, which is the library I talked about before. And we have now here our console error panic hook. That is actually the dependency we need to install here. We are simply activating this as a feature here so that it will be used. And then we are using vlog. I'm not 100% sure how all this works in the background. Maybe we will take a look at it later on to get it to work. This seems to be simply an allocator, which is quite small and can really easily allocate memory within the WASM namespace. Essentially, memory in a WASM or in a WebAssembly subsystem where the browser, for example, is concerned, is simply a linear block of memory. It can be allocated from within the WebAssembly code. So the WebAssembly instructions can allocate memory and say, I want so much memory, and they get this linear block, which might be resized to get bigger, to hold all the information needed, to data needed. Memory, this linear memory block may not be shrunk again during execution. So that is one of the things how WebAssembly works internally. And then we have this dependency here called JSys. JSys actually is a part of WASM bindgen, if I remember correctly, and this is the Rust binding part, which we will be using in order to get all this JavaScript stuff working. So this is essentially the Rust implementation of all the JavaScript counterparts, so that we can, for example, generate later on the data needed to talk to a canvas or to access the console or stuff like that. At least that is how I understood it. We will see if it's really working this way. And then is something here which are already actually here set there, that I want the features. The feature of this WebSys. WebSys is actually, or was it? Oh yes, JSys is all the JavaScript part, like the JavaScript standard functions and all that stuff. While WebSys, I guess, was the one which provided us with all the like the DOM objects, the canvas stuff, and all of that we can interact with this. And what I am especially requesting here is the image data, which is the data property which is used by a canvas, for example, to represent the data within a canvas. And we are going to represent, like, for example, lines we have rendered or blocks or stuff like that, to be able to transfer this then over to our canvas. So this is, as we know it, the Husky implementation to run our Clippy and test stuff and so on. And then we have something which I have been fighting. I know this is, I remember this is where I stopped the last time, was by default, this whole system calls something called WASM opt, which is a WebAssembly optimizer specific for this case, which makes the executable even smaller and faster and better and stuff like that. And it is usually called by default during the build process by Cargo. Unfortunately, this does not work yet on an M1 ARM Mac. And as I am currently running this on a M1 Apple Silicon ARM Mac, this does not work. And so I simply disabled it for now. We are not going to do some sort of production release or stuff like this. We just want to play around with it. So this may be even a spoiler here, or an information on this part. We are really just playing around with this. It is in no way intended to be a clean setup. I just want to get it to work and to render something into the browser, and then I would be more than happy. So we are just going to experiment with it, and it will be dirty and it will be hacky, and I will just clutter it together somehow to make it work. And this is essentially the target we are trying to reach here. So let's do this. Okay, so now we have all this stuff. The first thing I guess we should now try is to somehow have something that we can compile here and run in the browser. So this would be the first part, and for this I already started on the other side here as well. I created, let's do this here as well, because the documentation told us to. I created a www folder. So then I got some files there. So let's check what I have here in my folder on this side. I created first of all a package JSON. Yes. So let's, because we are going to use Webpack in order to render something, or to more or less bundle all our WASM and JavaScript and stuff together. There are a lot of different ways to do this, but the one page I found was using Webpack. So let's just create a package JSON here and put all this information in there. Essentially, we are just we have just created this one here, and we are just using this, where is it? Dependency. Yeah, we are just using Webpack, which is a JavaScript bundler, if you should not know. And we are using this plugin here for this JavaScript bundler, which is called WASM Pack plugin, which will then in turn use WASM Pack, which is another tool I have installed on my machine. Oh, I would have forgotten this. WASM Pack is a tool. Let me quickly show you WASM Pack. It's a Rust tool to essentially pack up and put together all of your different Rust stuff and create a WASM, a WebAssembly file out of it. It essentially does all the work and the heavy lifting for us, and this is actually where I got all this, how to do this, and let's use npm, and where do I get the setup here. And I guess I started with this template. This is essentially, I think, where all of this stuff comes from here. So yeah, it's like create WASM app git. I think I may have, I may have used this one, but it's mostly the same as a starting point, and edited around a little bit in it and so on. So we have now this, this WASM Pack plugin here, and we have Webpack here. And now let's copy our Webpack config here. I need a Webpack config. So let's do this. Let's get webpack.config.js, which will be essentially then our, let me quickly mark this one up and copy it into here. So we are essentially using this Webpack configuration, which is the configuration for our bundler, to tell it that we want different entry points here to be generated. For once, we want a Bootstrap.js, which will handle initialization, like where is the canvas to render to and what should be rendered, and put it all in there, and then have it start the whole process, load up the WASM file and stuff like that. And I have, from the start on, I have tried, after I built the first Hello World WASM, I've tried to get Webworkers to work, because I'm later on want to, of course, parallelize the rendering, because if we are only using one thread, this would be a problem. And even though if we are using one thread, we cannot block the main browser thread. You cannot really do this in a browser in JavaScript. You can, but you shouldn't, because that is the thread which is handling the UI as well. So if you do this, you have a completely unresponsive browser frame, and it might even give you this pop-up you may have seen sometime: the script is taking too long, should I kill it? And so from the get-go, I wanted to execute this WASM module, this our raytracer, in a Webworker, which is a kind of a thread which we can spawn, a separate process in the browser, which we can then communicate with, and to at least have it do the work, and then give us the data, which we can then just put in the canvas, and have this message passing between the things. And so the event loop will work, and there will be no blocking, and everything will be smooth. And later on, we may even be able to actually split this rendering up into more than one process to speed things up even more. So This is actually what is done here. So we have a configuration which generates us a worker.js because web workers need to have their own JavaScript entry point, which will in turn use this WASM pack plugin to take our Rust project. As you can see, I'm just going from the www folder here one level up, which will be our Rust project folder, and I'm telling it to use this crate and do what it needs to create the WASM stuff there. So this is actually how we are going to do this. We are actually creating this one, and we of course need then something we can open, which would be an index file. So maybe I should just copy this over. Let me see if I can just copy something from this folder. Let's for one check what I have in there. So, okay, and now let's copy certain files there. I want the index.html definitely. I guess maybe there will be, I guess, an nvmrc, which is simply a configuration for my node environment and which node version I'm using and stuff like this. Maybe there is a git ignore. Let's copy this over as well. So let's put this in here. Okay, so let's take a look at those files. I have this index.html here, and index.html is actually loading the bootstrap.js. So we should copy over the bootstrap.js as well, I guess. So this is simply a web page which has no real content, but just loads the JavaScript entry point. So what does this one now do? Yes, it essentially loads the index.js and gets more or less to work. So it just tells the system to import the index.js. So let's copy the index.js, and then we will see what I actually did in there. And so yeah, what is actually happening here? I'm using a library called comlink, which makes it a little bit easier to communicate between web workers and the main thread. It simply wraps this communication protocol which exists there and allows us to simply call functions into web workers. So the first thing we have here is a definition of the rendering size, which is the width and the height of our image. We remember it has the same dimensions. So we are telling it to render 2048 pixels width and height. And then we are creating an element within the DOM document of the browser, which is a canvas, and we are setting its attribute width and height to the size of our rendered image, so that it can actually accommodate the pixel size which our renderer will produce. And then we are doing something here which is a little trick to make it look nicer, because we are doing a kind of anti-aliasing now. So what we are now doing is we are using the CSS property width and height and setting it to half of the size in the width and half of the size in the height, which actually means that every pixel we are rendering will, 4 pixels we are rendering will always be blended into 1 later on, as we are shrinking the rendered target in size, which makes it a lot better in terms of output without us implementing any sort of anti-aliasing. We will see how this performs. Not 100% sure yet how this will work. So let's see. And now we are going ahead and adding this canvas to our document. We are getting the rendering context of this canvas, which is needed in order to put pixel functions there. And then we have finished our setup code, which is, as I've said, it's a complete experiment. It's hackish. It's not structured at all. It's simply there. It's setting up all this stuff and getting us ready to render something into a canvas. What we are now going to do is we have an asynchronous function here. Asynchronous functions in JavaScript are actually functions which are inside of the event loop, and they can actually be paused in between when we are waiting for certain event to happen and then can resume later on by the engine automatically. It's just syntactic sugar for all this callback hell you might have seen in JavaScript. So don't worry about too much. It's just a function. So we are calling this and we are telling it from which line to which line we want to render. So I have already accommodated here the fact that we want to render certain lines here so that we may be able to parallelize this in the future. So let's see. For now, we will do it in one worker and see how this works at all. I'm not sure yet. So what we are going to do here now is we are spawning essentially our Webworker. This is the way how you spawn a Webworker. You are simply getting a new worker instance and giving it a reference to the JavaScript file, which in our Webpack config we told it should be named worker.js. So it will be generated under that name and it will then be ready under that name later on. Then we are wrapping all this in the comlink so that we can then call functions on this worker which are exposed by the worker. We will see this in a second. So we are then logging something like, okay, I'm initializing a new renderer from start to end. And then we can call a function on our web worker, which is initialize the renderer. It is given the size so that the renderer knows what to render actually and in which dimensions. And then it is given a start line and an end line. And then we are starting the rendering here, and this is done by simply calling a function called render next on the renderer, because now it knows when it has to stop, when the finishing line has been reached, kind of. So we are just looping through all of this, and while this gives us data, we are always rendering and transferring one line of image, one pixel line of image. We are telling this thing to give us the next pixel line. This is essentially what our Rust code then will have to do, give us one line of pixels within our system. And then we are assuming that we get this data back here, this image data actually, in the format of the canvas of the HTML, which we can then use and put into our canvas, put image data, which is there is an image data structure. Let me see, image data JavaScript. Yeah, there we are. So it's actually, image data is actually just a data structure holding a kind of a binary representation. It's just a clamped array of 8-bit integers. So it's RGB data more or less with there it is. It's RGBA data with integer values between 0 and 255. So we are always having 4 bytes per pixel, which represent RGB and alpha channel. We won't use the alpha channel, I guess, we will see. But yeah, this is essentially what we then need to construct somehow in our Rust system. And then we need to return it. And actually, we need to tell the system where to start rendering this data. At the x coordinate, which will be always 0 because we are always rendering a full line, and then we are telling the put image data function which line it should have rendered. This is something which the render next function knows because it has rendered the line, so it is returning it as well and giving this to us as a number, and we can put it in there and render it. And then, in order to get everything started, we simply tell the system to spawn such a renderer now in a worker thread, in a web worker, from 0 to size, so for the whole image. So now let's copy over our render worker. There it is. And let's take a look at this one. What are we going to do here? Essentially, this is our worker code. I have this here. This is the syntax for the comlink, which is, as I said, creating this system to communicate between Webworker and main thread. And we are now going to have this init function here, which you remember here, which we are calling. Yeah, this init function, which gets the size and start and end. And essentially what this one does is it is going to import the package, which is essentially loading the WASM file, which is created by this WASM pack plugin. It will simply put the WASM stuff needed under this package folder, and we will be able to get it then there. So we are telling the system to dynamically load, because it has to fetch it from the, if we are hosting this on the web, it will need to fetch it from the web somewhere over network. So this needs to be some sort of asynchronous operation here. And in this case, we are simply telling it to import this thing, and when it's ready, to give it to us. And Webpack will automatically bundle this up correctly so that we are getting a initialized Webpack module here then. This is actually some sort of Webpack bundling magic here, and this is why we are using Webpack. So then we can call on the WASM module a function start. We will see how to get this to work. This is actually something that the WASM bindgen can do for us. Then we will create a new world, which will be a new struct inside our Rust code here. And we will use this line range, which we got, which is the start and the end range, and we will simply store it in this instance of a module. And we will set our current y, which is the current line we are rendering. And this is, of course, the start line. We need to start somewhere. And then we have our render next function, the one we are actually calling in this loop here. Yeah, there it is, the render next, which is actually then just checking if we have been gone over our range end, and if we have, we simply return false, so that this loop will end and we are ready to stop. And otherwise, we will tell our world to render the line y, and then we will create a certain return value here, which on one hand contains the current line, and we will then increment it for the next call, and our created data. So our Rust code will need to create this image data struct and put it in here, and we will have to ensure that we have some sort of world object, which we can here now create, and we will have this render function, and after we are ready here, we will return the red val. So this is all the kind of glue code which we need in order to have our system working here. And now what we are going to do is we are taking a look at the Rust code in order to facilitate all this. So in order to facilitate all of this, we need certain things within our Rust code. We need a certain amount of initialization, which I will just put here. So let's take a look at what we are going to do next. The next thing we need to do is some sort of start function, and this is where we are setting up actually this. You remember that we had our, where is the file gone? Maybe I should open it. We had this init here, and this init was calling start on the WASM module, and now we are essentially creating this start function, and the start function will be this one. And what we are essentially using here is this WASM bindgen, and we can simply call and tell it that we have a start function now. This is essentially a specific binding option here. It can have a start function, which will then be used to initialize the module. And yeah, we call it start because why not? And it's returning a result. Yeah, we are either returning nothing, so an empty tuple, which is the case when everything went well, or we are returning a JS value, which would be the error code or error we would be returning in case of an error. So what we are doing here is now installing this panic hook, which you might remember from the cargo toml. We had it here. It's this console error panic hook. And what it essentially will do, I will show this in a second because I think I'm going to try and run this, and it should then maybe show us an error. Is if the application panics, it should actually transfer this over to the console in JavaScript in our browser. And this is, I guess, the first part where we should or could try this. And if I am panicking here now and telling the system to, oh no, panic. So yeah, it's unreachable code. I know that. I hope it still compiles nevertheless. Or maybe I will just comment this one out so that it doesn't whine too much. And yeah, we don't need that yet, but we will see in a second. So let's try and compile this. The most easiest way should be in order here to use my Node version manager to get the right Node version and then have an npm install here, which should actually install all the different JavaScript dependencies we need, including the bundler. Let's just see if this works now. So it's installing everything, all of the stuff. Yeah, we don't really care about that. And now I should be able to do an npm start. And it should, as you can see, I've run the JavaScript building process, and it went ahead and compiled our Rust code. And essentially, we should now have here something like, we should now have a package folder here, I guess. Yeah, we have now a package folder here, as you can see, and there is a WebAssembly file, which is a binary file. I can't look into this, and it's kind of creating some sort of other surrounding stuff and code here, which will then be embedded or not by Webpack. I don't really care. The most important part is it has compiled our Rust code into WASM, into WebAssembly. And now we should be able to open up our browser to the given URL here, which should be somewhere here, like there. Project is running at localhost 8080, and if I'm opening this, you can see a blank page. If I'm opening up the console here, let's see, we may see, and we do, our panic here. So, and this is essentially what this module does, which we created there. Once the Java the Rust code panics, it will be transferred over into the JavaScript context, which is quite fancy here. That this is going to work so smoothly. We actually even get this stack trace here from within our more or less Rust code, and we can even kind of see what might have happened here. So this might even be a nice error, but as you can see, our panic here, oh no, panic add, and we get even the correct line definition source lib, line 32, and we are, I guess, here in line 32. Let me close this binary WASM file here again. Line 32, and there we are, there we panicked. So nice. So I will just leave the server open. It will automatically, by the way, recompile now if I change something. Okay, now of course this is not going to work because it expects a result and it isn't there. So let's comment this in again, and now it should compile again. But of course our JavaScript code will not work anyways because we haven't implemented our functions there. There is something like uncaught, in promise, type error, our world is not a constructor. Yeah, we are trying to, if you remember correctly, no, where is it? We are trying to create here a new world, something from the WebAssembly module, which is simply still not there yet. So I've just minimized it. It's still open, the terminal. We can get back to it and it will build in the background. At least I hope it does. Yeah, it does. So so let's get this to work. So now we have our start function and we have actually created our first WASM interaction system. So now we need something which would be our world. And I will simply hack in our data structure, which can be used within JavaScript in the communication with JavaScript to simply hold all this information we need there to go ahead and render stuff. So this will be our structure here, and we let me just why did I make this smaller? Let me just import all of this data types. So what we need is something like we need the size of the canvas to be stored. We somehow need an information about where our ray origin lies, where our wall position lies, wall size. All of this will go away in one of the next implementation sessions because we will implement a virtual camera and stuff like that. And we could really use this now if we had it already to do this. But I'm very eager to get this Rust WebAssembly thingy running, and I wanted to test this out simply. So yeah, we need this calculation like the canvas pixel world size. We need some sort of sphere to render somewhere. We need a light source to render, and so on and so on. So so now we are going to actually yeah, I guess implement this world. So let's do some implementation for all the functions that we need for our world. So for one, there will of course be a new function, because we need to, oh, that was, didn't I just copy this one over here? It seems to me I did not. So there we are. So we need a new function which essentially creates our world, and it creates our world taking all the little things we already implemented and putting it together, mainly in the same fashion as our last chapter did. Here our system, which essentially created a material and a sphere and a light and put everything together, and then went ahead and rendered all of this. So we are essentially doing the same thing here now as well. And we are creating it. We are having a new function which takes a canvas size and initializes a material, sets a wall size just to have it somewhere, and then returns a new world object. And the world object has a canvas size, which is the given one. It has a ray origin, which is fixed at the Z-5 position. It has a wall position at 11. It has the given wall size. It calculates its canvas pixel world size, the ratio between world pixels and canvas pixels. It has a sphere, which we are not transforming in any way, but using the material here, which we have defined, which has a color. We can change it later on maybe. Of course, we could make all of this configurable from the outside, but for now we don't even want that. We maybe later on we will change this. Let's see. Maybe we will create a bunch of spheres and render all of them in different colors. And let's play around with this once we get there. So now we are creating a light, which is somewhere positioned in the scene and has a color of white, and it's all there. So the first question now is, we have now all this nice and tiny and neat Rust code. And essentially this Rust code here is something that is, if you take a look, is more or less called here. We are telling the system that we want to instantiate a new object type world, and we are giving it the size. We are giving it the size of the rendering. And if you look here, that is essentially our new function. But the question is, how do we transfer this structure here, this information structure here, as well as this function into the JavaScript realm in order for it to be executed? And this is easily done, and it's really easily done, by simply adding WASM bindgen macros there. We are just telling WASM bindgen there, we want this world struct to be available, please, in WebAssembly. And we are telling it that we want to have the implementation available in the JavaScript world. And now we need to do something special, because now this new function would actually be available in JavaScript, but it would be available there as a function on the object world. And we don't want that. We want it to be a constructor. So we can simply tell it that we want WASM bindgen constructor. So we are telling it that this one is the constructor of the world object. And if I'm going to compile this now, it should already have been compiled. Let's take a look at this one and reload it. We can see that now the initializing actually worked. So before it told us that it couldn't find the world object and all of this stuff, but now it can. And this is quite fancy actually, because now this call and this call already worked. So what is this world now? Let's take a look at this world in the JavaScript world, in the JavaScript side of things. I'm not 100% sure that this is working. Yeah, it is. So what is this? Yeah, it's actually some sort of pointer, whatever. It's something which is pointing into the Rust world. And as we haven't exposed any of the properties really, we can't see it there. But if we were to, for example, have this one public, we should be able to actually see it here. No, we are not. I guess this is somehow transparently done. I should be able to access it. Let's see, maybe I can. So what is if I'm logging world canvas size here? Is it then giving me it's compiling, is it then giving, yeah, it is giving me actually here the right value. So I can now actually access this data which is available here. There is JavaScript wrapping code around all of this so that it has this pointer object into the Rust space where this world lives. And is still able to access it. This is the magic of WASM bindgen, which is working there, and I think it's absolutely awesome. So let's just remove this here again. So now we have this new function implemented, which actually creates our scene for us, kind of. Now we need to implement the render function, because this is called on world and it is given a line and it should render a line. And essentially this is kind of easy for us, because we already have code like this. We are doing this in our code here. We are actually calculating all of this for each x, y, and so on, and we only need to do this now for one line. But let's just paste it in there and quickly take a glance at it. So we have this function there, and I don't need to specify that I want to export this specifically to WebAssembly here now, because it is defined as public. And I have this WASM bindgen macro on top of this world implementation block, which means everything in here which is as public will be exposed. We only needed it here to specify we want to expose a constructor. So here is now something new. We will return a WebSys image data. And this is another really cool thing here, as actually. This is it's already linking the MDN documentation. This is the JavaScript image data thing we already saw, the JavaScript side, implemented in Rust and with a layer in between to interchange these types. So it is completely transparent handled for us that this is somehow put into memory in the most efficient way in the WebAssembly memory and then transferred over to JavaScript or the other way around as we are going to need it. So we are essentially telling this function that we are returning as a result an image data or an error again, but we will be returning image data. Yeah, and what we are going to do here is we are actually initializing ourselves a vector of U8s with a specific capacity we already know, because we know that we want one line. So we want the pixel size, the pixel amount of canvas size, one line, one row, and we want this times 4. Because we need RGBA, which is 4. So we need 4 bytes for each pixel. So we can initialize this here. And actually, we could either create a vector of the needed size and then kind of write a 0 into every of those positions there. But we can, this is why I'm using this unsafe block here. I've not really written upon it. I've just Googled it and inserted it there. Because we know that we will overwrite each of those values later on, we can simply ignore that there might be now random data in this memory area where our vector is allocated. So we don't care about that. And what we are then going to do is essentially just iterating x here now, because our y is fixed. We are just iterating the width. So, and doing all of the different calculations we did before as well. So we are calculating the world x and y position. We are calculating then the point on the wall, on our virtual wall, where we're projecting the image to. We are creating an array, and there is obviously an import missing. So let's fix this, and there is some sort of import. Yeah, the intersectable is missing there, the trait. And there is something else missing. There is the illuminated trait missing. So what we are now going to do is we are creating our array, which is pointing from our array origin through the scene onto the canvas point we want to render. We are then calculating the intersection of our one sphere, which is our scene currently, with the array. We are getting the hit information, and if there is a hit, we are calculating Phong shading for this hit based on our given material, or better said, we are calculating lighting, but we only have implemented Phong lighting yet, so we are calculating it. And this one actually is just to have Clippy shut up, the linter shut up about this +0 here, because it thinks this is shouldn't be there because it is an addition which does nothing. So, but I want it there for readability. So what I'm now doing is I'm actually taking the x coordinate we are currently rendering. I'm multiplying it with 4 because we have 4 bytes per coordinate. And then I'm writing the first one of those, the second one, the third one, and the fourth one. The alpha channel, the fourth one, actually is always 255. It's always completely opaque. I want it to be seen. And the other values are simply the fragment color. So the rendered color of this specific ray, the red part, the green and the blue part, multiplied by 255, because we need to transfer them from the range 0 to 1 as a floating point into the area 0 to 255 as an integer value. Because that is actually what this data structure needs to be. And then we can use this image data thing. And as I said, there is already, for all of this stuff, there are the proper tools to convert between the different datas, like the Rust part and the JavaScript thing. And this is actually the image data from this websys. And it has a method new with U8 clamped array and sh. which is the size, the horizontal size. So we are actually telling it there is a data structure here and it needs a clamped array, so it knows that this is filled with 8-bit integer values it can use, and which we just created here, if you remember. So, and we have the canvas size, which is the width, which is 1 line, and we have the height of 1, which is the height of 1. So this is what we are returning there. And this is actually what, let's check. No, where did I again close it? Where is our, there it is. So this is actually what I'm getting there. I'm getting this image data. I'm putting it into one function here with the y, and I'm returning it from the worker. And essentially, this should now work. This should now render data, because this function in our Rust code will be called for each line of the image. The image data should be taken out of the Webworker. The Webworker should, the data should then be rendered into the canvas, which we are doing here in the index JavaScript file, if you remember. And yeah, then the next line should be rendered, and this should be done until we are finished. So let's take a look at if this actually worked. And you can see here in the background there is a sphere, so it seems to have worked. So let's reload this. And as you can see, it is live rendering our sphere. And if this isn't awesome, I don't know what is awesome. This is running in the browser. It's using our Rust raytracer code, and it's rendering a sphere. It's absolutely beautiful. So first I thought maybe I could speed this up but it's quite fast. You have to realize that this picture, which was just ray traced, is 2048 by 2048, and not what you can see here, the 124 by 124. So it's 4 times this big actually, and it's rendered amazingly fast. So, but what we could actually do is, now that we have this, is why don't we make this color of our lightning configurable? Should be easy to do. So we could say, okay, we want a new world, and we are just putting a color in here. And the question here is now, what would we do? We could expose our color now here using WASM bindgen, but I guess we will simply do something like, we want a red, which is an F64. We want a green, which is an F64. We want a blue, which is an F64. And we will then just put those data points, red, green, blue, here into our code. And we will change up our, where is it? We will change up our world here by, first of all, let's just check if this is working. Let's create a yellow sphere. Let's save this. Let's see. Okay, and this is working. Now I can control the color from the JavaScript space. So now let's expose this to our main function, which creates those workers. I like that. So, and actually this now here can be an object which we put in there, RGB, and we are just giving it here RGB. And now our index.js can spawn a renderer, and our spawn render function should now, I'm not 100% sure, as we are not using this. Let's just put the color in here, I guess. We are not yet using the multi thingy part, and it always uses 0 and size, which is no, the renderer will always use let's just do start is 0 and end is size, which is a global variable here, so it's accessible there. So we don't need this here anymore, but we need the color now because we want to put it here. This will be our color. And now we can do R is 1.0, 0.0, 1.0, for example. So RGB. Let's save this. Let's render it, and we have a pink or magenta or whatever this color is called, sphere. So this works as well. But now we could actually do something more interesting here, couldn't we? We could actually combine this canvas creation with our spawn renderer thing and have something like a create or render a sphere function, which then in turn creates such a canvas. So maybe we could do this, and I guess I would like that. So let's do this. Let's actually put this in here, I guess, or let's make a function called function create canvas. So let's get this out of here and let's return the canvas here now. So let's get this here, I guess. Oops. There is the context now. So canvas create canvas. Let's just check that our code still works. Yes, it still renders. So this is nice. So now we should be able to, let's maybe say we want the 256 size, which would make it a lot smaller. Yes, and a lot faster, of course, to render. But now we should be able to, let me check, because we now should be able to spawn more than one of those. Let's just try this. And now we have a lot of different canvases, which, as you can see, are spawned in parallel and are rendering in parallel there, which is quite awesome. So now let's maybe kind of do something like math random. Let's just randomize the colors, and let's just see what is happening then. Yeah, maybe let's do this in a loop so that we can better control it. Const sphere count. Let's say we want 16 spheres, and so let's just do a for let I 0 I as long as I is smaller sphere count. Let's call this code here. Come on. So if I now save this one, it should actually, it doesn't work. Okay, what have I done there wrong? There's something, I've broken something. So let's take a look at this one. Error importing initialize module path failed. What? Spawn renderer? That's something I did wrong there. Yeah, I removed the curly brace there, which should have been there. So yeah, and as you can see now, we have a lot of different spheres rendered live via our ray tracer into this system. And as they are now this small, we might actually change this up and have them the real size we give them, so that we can actually tell them to be only 128 by 128. And as you can see, they are not looking this nice now. As you can see, they now have an edge here, this because it's not that fine rendered. So let's switch back to our pseudo anti-aliasing. So yeah, I love this. This is absolutely awesome. So let's maybe see how many spheres would actually fit in this browser. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yeah, I could have guessed that because I rendered 16 and 2 are here, so it should be 14. So 14 by maybe, let's see, 1, 2, 3, 4, 5, 6, 7, maybe 6. So let's maybe put 14 by 6 spheres here. And I guess this is horribly inefficient now because we are actually really rendering all of this in parallel and spawning web workers for all of them simultaneously. So we could actually maybe speed this up if we only spawned like the number of processor cores we have web workers, which we could do, and then have this stuff render then those in series. But yeah, I'm not 100% sure. But yeah, we could actually do this. We could chunk this up, but why should we? Let add another line here, I guess. And what's kind of interesting is why do those things have some sort of margin? Let's set this to 0 and let's see what happens then. So now they should actually be directly. Why are they? Let me see. Why are they having this? What is this? Why do they have this spacing there? Where does it come from, actually? That's interesting. Where is this spacing coming from between the different lines? I don't get that. Oh, and we did we do something bad here? Did we somehow crash our? No, we did not. Something kind of. Okay, what did we do here? Something bad happened there, or is happening there? Not 100% sure. But yeah, strange. This is actually the WDS is actually this development server which takes care of all this. If the code has been updated, it will re-render and stuff like this. So maybe this is just a problem there because our spheres have been rendered beautifully, but I'm still not sure why and where this spacing is coming from. Is there some sort of okay, let's just pick one of those and let's get the computed properties and let's see. So there is no spacing there. Strange. I guess we could maybe easily fix this with a hack, and this is exactly what I will do now because it's kind of I don't really like this. So let's have this. Let's have some style here, and let's just tell the body the background color is black. So yes, now this looks absolutely amazing. I love it. We are rendering like, I have no idea how many, but it's just awesome that we are really ray tracing this live in our browser, multi-threaded in web workers with such minimal effort, and we can reuse our ray tracer code. And I think maybe I will update this in the future while we go along from time to time to have it actually work in the browser because I really much like it. So we could even kind of maybe change up a little bit more, like the position of our lighting there. Maybe would be yeah. Why not? Let me see. We could do this by putting more information in here. I know this is not the nicest way of doing this, but yeah, why not? Light X will be F65. We should actually, with each change that is done here, the code is recompiled and it is re-rendering all this in the background. So my system is kind of, yeah, let's maybe just render one sphere here, because this can easily be handled. No, there we go. So now there should be one sphere, nice one. So this is not that processor hungry then. Light X, light Y, light Z, I guess, which is an F64 as well, and an F64 as well. And now we are creating our light source at light X, light Y, light Z. And I guess now I'm putting this in here as well. We need to transfer it here then. So let's call this X, Y, Z. And transfer it over X, Y, Z. So now we should be able to, where are we creating this thing? We have this color now. So let's maybe get light. Yeah, light. Let's just call it light and we transfer it light. And now we are creating, let's refactor this out here. Let's put the color there directly and spawn a renderer with color and light pos. Yeah, I guess we should call it light position or light pos or something like this. Light pos, light pos. And let's create this one. Const light pos is, let's maybe create a function here, function random. Let's just call it random, I guess. Could be an arrow function, which takes a value with, yeah, let's call it start and end. And it will give you a math random multiplied by, let me think, end minus start plus start. This should actually give us, a random value between start and end, a floating point random value, which is absolutely okay for us here in case of the light position. And I guess I want the light position then just to be X between, let's see, random between, let's say, -10 and 10. And actually I want this for each of the coordinates, and then we will see how this will, this would be a Y, and then we have a, Z here, which is a random between -10 and 10 as well. So let's reformat this. Let's re-enable our multi-sphere count here and let's re-render this. And it doesn't seem to work anymore. So maybe let's see what we are doing here. Let's kind of console log light pos. Maybe we did something wrong here. Don't know yet. Let's see. Console rendering. So it tells us that it is rendering object -0.4 something. There is something wrong. There is a coordinate missing, definitely there. So, oh, I should have done X, Y, Z and not, yeah, and this is, now we are actually getting differently lighted up spheres. That is actually quite nice. Maybe we should have the Z coordinate between -10 and 0 so that it is always in front of the sphere and not behind it, because that would kind of look quite not so nice, because it would be very dark. So yeah, so now let's pump up the sphere count again. Let's save this, let's have it render all of this, and let's let's look at this while it renders our different spheres with different lighting and all of that. It's just amazing. I really like that. I'm really having fun doing this and taking a look at this, and this is just awesome. And actually this picture is looking completely wrong because all of those now have a different lighting angle, and it just looks it's just kind of getting slight problems with my brain looking at this, but somehow it looks awesome. It looks absolutely awesome, and I love it. That's great. I love it. Let's redo this. Let's re-render this. Let's render another one. Okay, there are some. Didn't they render, or are they simply black? I guess they didn't render. Maybe we still have some sort of problem with the really big amount of web workers I'm spawning there. So yeah, now they seem to all render again. Yeah. So yeah, maybe there is a problem there, but nevertheless, I'm quite fascinated by how fast this is, how fast this stuff renders. That's actually something I'm really amazed about. I really love that. So this is great, and the kind of integration we have, like this immediate, we can program the code, we can type it in, and we can adapt our bridge, and it's automatically like recompiling stuff and reloading everything and giving us the experience inside the browser is great. It's just the same as with modern JavaScript development, but I'm writing Rust code in the end. This is awesome. This is absolutely awesome. I love it. So yeah, I will of course put all of this stuff in the GitHub. It will be in the experiments WASM branch. There will be a separate branch for that where you can take a look at all of this and play around with it if you like. And I hope you had as much fun doing this as I had implementing this in the first place. So I'm just thinking this is absolutely awesome and gorgeous. And while we are talking here, I will have it re-render. I just love this this ease of use, and I'm still loving Rust for actually making this possible. And yeah, this is just, I just love it. So let's sit back a little bit here and see for the next image to be rendered fully. So yeah, thank you very much for joining me here. As I've said, I hope you had as much fun as I did, and maybe I will create a background out of this. I don't know yet. It looks nice. And yeah, I hope you enjoyed this bonus session here. And in the next one, we will actually, as I've promised before, go further along creating our scene and world object and creating a camera and stuff like this, which will then allow us to actually define a more complex scene consisting of multiple spheres and stuff like this, positioned somewhere in the world, transformed, and a camera looking onto this scene from a specific viewpoint and then rendering out this scene. This will what we will do in the next episode. So I'm already looking forward to this, and thanks again very much for joining me, having this much fun. And if you like this as well, please subscribe and give the video a thumbs up if you like it. I would really much enjoy this, because I'm always enjoying if you are interacting with me. So please give me some comments about the video or other videos, what you want to see in the future in case of these bonus videos and experiments. I would be glad to have some input there. And yeah, I'm already looking forward to see you the next time. So thanks, and have a nice day. Bye.